I'm Pieter Schaar from University of Amsterdam, who will tell us about universal behavior of non-minimal models of inflation.
Okay, thank you. Very happy to be here. Can everybody see me? So we need to turn off a light. I don't know. It's fine? Okay, good. So, when I got invited, for a while I had to think what to talk about. It was not so clear. There are a couple of things I could talk about, but then I decided in the end, for several reasons, that I want to talk about this kind of stuff. I was warned or advised that I should start with a very general introduction. There might be PhDs or master students in the room, so I'll keep the first 20 minutes probably very broad, and then we'll see how it goes. The reason I picked this particular topic is initially I was not so excited when I started working on this. I was not so excited about this. I actually thought there was something very wrong about it. But then, I asked my PhD student to work on it, and he came back and he got really excited about it. And it turned out that there's something interesting about this that I will try to explain to you. So he got me interested in it, and I also think this is the excellent occasion, because he will graduate this year, to also promote him a little bit. Okay? So that's also a reason why I want to discuss this topic. So his name is Benjamin Mosk. Everything I say and that's wrong, that's not his fault. So you should keep that in mind. So let's start. And before I start, I actually have some other thing that I need to do. I couldn't resist doing, because I came to the CP3 Origin Center. I looked at your website and I thought this looks very similar to what we have been doing in the Netherlands for the last year or so, where the Dutch theory institutes in Utrecht, Leiden and Amsterdam got a big grant for 10 years to collaborate together, to hire new faculty, to try to promote all kinds of activities. I think this is again the excellent occasion at this point of the year to also point this out to you. It's called the Delta Institute for Theoretical Physics. And there's a nice story about why it's delta. It's a nice mathematical symbol. The triangle in the Netherlands between Amsterdam, Utrecht and Leiden forms a delta. And delta is also the name for that region of the Netherlands which is below sea level. It's more or less overlapping with these three places. And we were very careful in developing a very nice logo. This is relatively new, so I'm doing this little test all the time when I show this logo. Do you see the triangle? Yeah. Okay, good. We were a bit in doubt a little bit. We also actually made pens, just like I noticed because I got one. CP3 has been, you can write on an iPad. It's very similar. So I think I can learn a lot because you're a little bit older, so I'm going to ask Martin, I guess, a lot about CP3. But seriously, what this is important for is the following. As of last year, so I'm more or less the coordinator manager of this initiative. So I'm like, in Dutch we call this, we have Sinterklaas. I'm Santa Claus because I can hand out all the money more or less that we have obtained. And there are many opportunities that we can now try to achieve. We have every year we have many postdocs and fellow positions. We can hire many PhD students. We hired 6 new tenure-track faculty in total, and 2 in each institute. There are mini workshops, there's extended visitor programs. All these things, you take your pick if you think anything looks interesting, just write me or write somebody in the Netherlands that you know in any one of these 3 institutes. And I think there should be a lot of possibilities for each of you, okay? More information can also be found on the website, of course. We even, of course, have a Twitter, and nowadays you have to have a Twitter feed, you have to have Facebook, etc., etc. So that's enough for the advertisement bit, but keep it in mind. So what's the plan for the talk? So what I hope to do in the first 15-20 minutes is to give you a very general introduction to inflation and non-minimal models. Now, I don't think in this environment I need to tell you a lot about inflation or why it's considered a good idea, but I'll briefly remind you. And then I'll move on to non-minimal models. What do I mean with non-minimal models? What can we learn from them? Why do we look at them? I'll briefly say something about strong coupling, Starobinsky attractors. So if you open this can of worms, if you are going to expand the landscape of models that you're going to look at that can give you inflation, then you might think, okay, why would you do that? There are plenty of models already, but it turns out that in this particular subset of models, these non-minimal models, there's some interesting behavior, some universal behavior that you can try to quantify. So I'll briefly remind you about some work that has been done over the last years that shows that actually there's a strong coupling limit in all these models that reproduces exactly what is known as a Starobinsky attractor. I'll also remind you what that is. And then I'll come to the bit that we did. We basically looked at the weak coupling regime, and it turns out it also shows some universal behavior. It's called, in fact, it's chaotic in the weak coupling limit, and I'll also try to explain to you a little bit more what that means. And then I'll end with a summary, and these figures at that point will also be clear. Okay, good. So let's start. General intro. So what I hope to achieve in this general introduction is to, I'll briefly remind you the case for inflation, to give you a short history of non-minimal models, which is quite interesting. I didn't know about that either until recently. I'll briefly talk about the connection between non-minimal models and pure gravity. And what was our motivation to have another look at these models. Okay? So I think you probably are all familiar with why we think inflation is a good idea. I'll just stick to the most important thing from my point of view, and that is that actually it describes the data for the scalar perturbations that we've measured in the CMB, for the density perturbations in the CMB, like a Schaar. Okay, so if you look at this plot, this works very well. So it just predicts very nicely all the structure that we see in the universe, and I think that's probably the most convincing motivation to look at inflation. We don't have many alternative candidates. And these are a couple of the things that we can try to measure. This is the scalar spectrum, and you know that actually there's some amplitude, and then there's some dependence on the scale that you're looking at. This is very weak, it should be almost scale invariant. This is measured by the spectral index. The spectral index is expressed in terms of slow roll parameters, and these slow roll parameters tell you something about how the scalar field that is responsible for the accelerated expansion is flowing, is rolling in this potential. So these parameters, eta and epsilon, tell you something about the potential that you're looking at. Okay? And then of course there's also the tensor to scale ratio, which is just the ratio between this, and that caused a lot of excitement over the last half a year, but we should apparently we have to bury that excitement, because it seems that it might be a bit premature. But in principle, if you can measure this one as well, this tensor to scale ratio, you have another handle on what the potential looks like of inflation. Okay? Now, and here's this nice little plot that will come back over and over again. That's why I also mentioned these two parameters. NS, the departure from scalar variance, and the tensor to scalar ratio. You can look at the data and then try to put confidence levels. These are two sigma contours in the NS versus tensor to scalar ratio diagram. We've measured the departure from scalar variance, so it's 0.96 approximately, and it's not 1, so we've definitely seen that it's not equal to 1, which is a good indication of inflation. And we have not measured the tensor to scalar ratio, but we can put certain bounds. Okay, so we know it has to be smaller than 0.2, roughly speaking. Okay, and of course, again, I said 2 suggested that maybe should sit here, but it turns out that that might be dust. But nevertheless, these contours will come back, because in this plot you can actually put this whole family. I mean, in fact, in principle, you should we should agree that inflation is a paradigm, okay? So we don't really know how to, from first principle, come up with a very definite prediction that will give you a dot in this diagram. So there are all these models that that you can actually that have been plotted here in this diagram. There is all kinds of chaotic models in this diagram. There is Starobinsky model is here. So there's this whole plethora of models, and you should look for, basically the data tells you in what direction to look, but in principle we should actually get more theoretical information of, I think, that's my opinion, that where to look. And this is just, anything goes as long as you agree with the data. Good. So I think you've all heard about this. And that there is this whole, there are all kinds of models of inflation that you can think about. So, and then of course there was this. I already told you that this has gone away, but nevertheless I just briefly want to show you this because it played a role in the motivation for what I'm going to tell you. So apparently Bicep 2 found some remnant in the polarization of the CMB that's this beautiful picture. There's nothing wrong with this picture, but this arrow, there's something wrong with that. They associated this picture with primordial gravitational waves, and most likely that's not true, because most likely it turns out to be dust. Nevertheless, if you were to interpret this as primordial gravitational waves, there would be on top of these two sigma lines that are actually produced by the Planck satellite on the previous slide, there would be another region which would be preferred by Bicep, which is a bit on the high side, would suggest a best fit value of R equals 0.2. That was really exciting at the time, because of course it would tell us the scale of inflation, which would be around the gut scale, which would be awesome if that were the case. We would have a probe, and we would really be testing gut scale physics. But as I said, most likely this turns out to be dust, so we're not sure if this is really the case. Most likely this will just go away or go down. Okay? Nevertheless, I wanted to show you this because it played a role in some of the motivation for the work we did at the time. So, if you talk to somebody who's working on inflation, then most of the time they will tell you, okay, I'm looking at single field, slow roll, minimally coupled. So just an ordinary single scalar field that's minimally coupled to gravities, and which behaves in a slow roll, which its dynamics behaves in a slow roll fashion. Now this is an example of what I would consider Occam's razor. It's just the simplest thing that you can look at, okay? So first understand the simplest thing that you can look at. It's also the thing that can describe the data very nicely, so let's first try to understand that. But I think it's very important to realize that we don't understand from a theoretical point of view inflation very well, and we have to think about UV consistency. So how to embed inflation into a truly quantum theory that includes gravity, etc., etc., and to understand, for instance, the fact that there are all these fine-tuning issues. If you want to get inflation to work, then you better make sure that the effective mass of the inflaton is much smaller than the Hubble parameter, the scale of inflation, and this is just a bit unnatural. You would expect quantum corrections that actually bring you up to this scale. So we need to really understand this, and for that we need to think about the UV embedding. Now, if you think about the UV embedding, then there are several ways, of course, to go about. But in particular, typical UV embeddings would suggest that you add more scalar fields, that there are simply more degrees of freedom. If you go to higher energies, if you follow IG flow, you would typically expect more degrees of freedom, so you would expect perhaps multiple fields. You might also expect, or you might also consider, non-minimal couplings. There's no rule that tells you that you shouldn't do that, And in fact, this might be an interesting route, as you will soon see. Of course.
Is that within the, sorry.
Yeah.
Is that within the Occam's razor?
No, so this is outside Occam's razor. So the question is, why would you actually restrict yourself to the single field, slow roll, minimally coupled? So from a theoretical point of view, UV consistency is one which tells you something about, most likely multiple fields is a good option. But then second of all, and I didn't mention that as of yet, observations are perfectly consistent with adding more degrees of freedom, more fields. I mean, if you think about it, there is no direct constraint on the number of fields that are active during inflation. So there's plenty of opportunity to consider more than just one active light scalar field, which is also in line with reasoning from a UV point of view. String theory in particular also suggests that there should be more than just one scalar field. Now, why would you do that? Because we have trouble enough already with the big class of theories that we have. I mean, there's all kinds of, there's this inflationary zoology. There's all kinds of ways to reproduce the data. There are all kinds of models. And of course, we hope that the data will zoom in and constrain all these models a lot better in the future. But I think it might be a good thing to first try to expand your parameter space and then see if you can find some organizing principle. There are so many things that we don't understand in a way that it might be good to think about expanding your parameter space even more and seeing if there are some organizing principles at work to try to organize the different models that we have. So that's one thing that I started thinking about. And the thing that we're going to look at in this talk in particular is to generalize single field, slow roll, minimally coupled by adding a non-minimal coupling. Okay? So what is a non-minimal coupling? Well, we'll see an explicit example later on, but it's basically saying that we're going to couple the scalar field to the curvature scale. Okay? There's going to be an additional term in the Lagrangian. And it has a rich history, in fact, that I wasn't completely aware of when I started working on this. And I've just listed for your convenience some old papers here that for those of you that are interested you can look up. But the reason they were interested in this in the early 80s, the late 80s, beginning of the 90s, was that spontaneous symmetry breaking was of interest. And if you add the non-minimal coupling, basically what you do is you're going to say that the Planck scale is going to be induced spontaneously by having it being connected to a vacuum expectation value of a scalar field. Okay? And that sounded interesting, so people were looking at that from that point of view. So they're looking at spontaneous symmetry breaking, inducing it in Planck. And when they did that, they also realized that in this process of spontaneous symmetry breaking, you could get inflationary behavior. It sounded like an additional bonus. Another reason they looked at why they looked at non-minimal couplings is that when you would look at certain inflationary models like natural inflation or chaotic inflation, then it's well known that the parameters in these Lagrangians have to be very fine-tuned. So you have to make them very small for inflation to operate consistently. And this could be ameliorated by adding a non-minimal coupling. So if you would add a non-minimal coupling, if you look at these papers, for instance, Fakir and Undu and Kaiser, they concluded that the fine-tuning would go down. The specific fine-tuning for the parameter and the potential would go down. Of course, you've also added something. You've added an additional coupling between the curvature scalar and the scalar. But nevertheless, this was what they thought was perhaps a good idea. Then, of course, there's the connection of non-minimal models to Starobinsky's R plus R squared. Now, I don't know how many of you have ever heard of R plus R squared models. So Starobinsky already in the early 80s, 1980s, proposed that actually you could get inflation to work without any scalar field. Okay? The only thing you needed was an R squared term. So it's a higher order curvature term that you would add. And if you look at the dynamics, if you look at this original paper, actually that's quite technical and even, I would say, somewhat incomprehensible. But actually there's a very nice connection between R plus R squared to non-minimal scalar field. Okay? And for those of you who don't know about this, I will briefly remind you how that works. It's very simple. And that was actually also pointed out by Witt later on. So this R plus R squared model is actually equivalent to a non-minimally coupled scalar field model. And later on, this is already in the 2000s, of course, people became very interested in trying to connect the Higgs potential to very high expectation values to see if the Higgs could also give rise to inflation. Okay? Now, to be able to do that, you also have to add a non-minimal coupling. Okay? So otherwise it doesn't work. So that's more or less all the different ways that people have thought about non-minimal couplings and why that might be a good idea. Okay? Now here you see more or less, well, this is exactly what we're going to look at. So we have a scalar field potential U of phi. This is in the Jordan frame. This means in the frame where the scalar curvature has this omega in front, which depends on phi. And we're going to look at this action and see if we can come to some very universal conclusions about the properties of these models if you're interested in inflationary behavior. Okay? So all the stuff that I have been discussing here can be written in this particular way. The interests that I've just listed they're all part of this Lagrange. Okay? Is this clear up to now? Can I go faster? Should I go faster? Well, we'll see. Good. Right. So this is just for those of you who have never heard about R plus R squared, Starobinsky's model, and how it is related to non-minimal scalar field models. It's actually quite simple. In fact, it extends beyond R plus R squared. Okay? It is actually true for any function of the Ricci scalar. So you have an action that includes a genetic function f of r. Okay? And this is equivalent to a non-minimally coupled scalar field theory. So how does that work? Well, what you can do is you can add an auxiliary scalar field. So this action, I claim, is equivalent to this action, where f of r is replaced by f of a psi, which is an auxiliary scalar, plus the derivative with respect to the scalar of this function f of psi, times r minus psi. Okay? Now the point is, of course, that this is auxiliary, the scalar. There's no dynamics, so what you can do is you can solve the algebraic equation for psi. You find that r equals psi, and then you get back this action. Okay? So these two things are equivalent, obviously. So if you solve for psi, you get back this action, but you can do something different. You can introduce another scalar, which is actually equal to the first derivative with respect to psi of this function f. So if you define this phi to be equal to the derivative of f of psi, then psi is a function of phi. Right? You need to solve this. You get psi as a function of phi. Putting that back into the action, you will have a first order. So you will just have this first order appearance of r. Okay? So if you do this, then what you get is an action that looks like this. R times phi minus v of phi. Where this potential of phi, if you plug this in, is a particular expression that depends on f and it depends on this psi. Okay? So So I haven't listed it here, but this is, so this particular, so you should realize that this potential can just be read off if you solve these equations. So now the point is that this apparently is equivalent to that. And this is of course just an Einstein action. So any f of r is equal to this action, which is now non-minimally coupled because this phi times r is now coupled to this Ricci scalar. Okay? Is that clear? In fact, if you plug in, so in general it's very hard to engineer for any arbitrary f of r what this potential looks like. But for f of r equals r plus alpha r squared, you can do this. You can solve all these equations, and you get for the potential this expression. Okay? So the potential then looks like 1 minus e to the power minus square root 2 kappa over 3 times psi. Okay?
What is psi?
Psi is actually the scalar field. Okay, so I should explain that once you end up with this action, what you can do, of course, you can redefine your field to turn this into an Einsteinian action, so a minimally coupled action, and then you get, this is achieved by defining properly what you mean with psi. Okay? And in this action, you get this potential. Okay? So this action with this potential is equivalent to r plus alpha r squared. Okay? So, in other words, you get exactly the same behavior if you analyze, for example, where this potential would lead to inflation. You would get exactly the same behavior as what you would expect for r plus alpha r squared. Okay? And in fact, what this potential shows, this potential has a plateau. It's a very steep plateau, and that's where you can inflate. And so this seems to be a very nice way to get rid of your scalar fields and just describe inflation by a pure gravity action. There's one slight issue, and that is, of course, that if you want to inflate using just pure gravity, you have to make sure that the r squared term is relevant. I mean, it has a true influence on your dynamics. So it means that there's order 1 higher curvature correction. The alpha in this expression is order 1. Okay? So it's not small. If it were small, to first approximation, it would just be ordinary Einstein gravity, and you would not get inflationary behavior. Now, if this coefficient is large, or order 1, there's no good reason why the other higher powers are not there. Okay? So there's a naturalness problem. Okay? Is that clear? I mean, you have to explain, if you say that this is order 1, you have to also explain why r cubed, r to the 4th power, why all those terms are absent. You have to fine-tune the way. Okay? So this sounds very nice, but it's not, you know, from a UV, high energy physics point of view, there are still some issues. Now, the nice thing about these kinds of models, are pure gravity, so r plus r squared, is that in fact, they sit in the sweet spot, and that was only realized, I guess, since 5 years, because Starobinsky, of course, wrote down his model 34 years ago. I don't think many people paid much attention, although it was known. I mean, I heard about it. But since 5 years, it suddenly became more interesting, because actually Starobinsky, if you fix the number of e-folds that you want to get out of this particular model, lies exactly here. So it has very low tensor-scalar ratio, but the spectral index is right where it should be, if you look at the Planck data. So people would say, okay, Starobinsky is in the sweet spot of the Planck data. So we should go back and study it more carefully, perhaps.
But before all this, I mean, people were saying that in hyperinflation, you wouldn't have large sensor nodes, and people would go on and argue that from a particle physics point of view, hyperinflation would be the most natural thing, and so on.
Sure.
So it seems like a sociological phase transition. No?
I completely agree. So there's no, I mean, this is not a convincing reason to look back at, to go back and look at
I
Starobinsky,
think it's
as far as I'm
because
concerned.
the Higgs inflation model that people started to pay attention to.
That's also true.
Right.
Yeah, I should mention that.
The logical phase transition was that model, and I mean.
I haven't mentioned that yet, but indeed it's true that if you look at Higgs inflation, it is exactly, you get potentials of this type, okay, at large scalar fields. So it indeed reproduces this prediction. So it's in the same region. So that's also a reason why suddenly this came back to the front. But I think it's also true that some people, at least that I spoke to, they go back and look at Starobinsky as an example of something that is very simple, in some sense, only has 1 degree of freedom, just gravity, r plus r squared, that can do a pretty good job of describing the data, of course, with all the caveats about fine-tuning. I don't know. So I just wanted to show you this because not everybody might be familiar with this equivalence. It might be fun to know.
Can you get a hybrid-like model with 2 fields from pure gravity or not?
No.
No.
No, it's always 1 additional scalar field. It's 1 additional degree of freedom that you introduce through these higher order corrections. So hybrid, you mean 2
No, but
scalar.
in some sense, in the most general FOR, you could have any powers of gravity, right? So
Yeah, but you always get 1 additional scalar degree of freedom.
No, why is that?
Why is that? Why is that? Well, essentially because all the higher, all the higher order behavior, if you just follow the logic here, can be captured by 1 scalar field that just depends in some complicated way on the auxiliary scalar psi. So I don't know if I have. Maybe that's not a good explanation. It's a technical one. It's a mathematical one. It just follows from this procedure. So I think. Let's see if I can come up with a better explanation. I have to think about that. I don't know. Maybe there is a better explanation for why there's just 1 additional degree of freedom. There should be 1. Yes.
Do you know if there are other inflationary models? Let's say other models with, say, just gravity, but maybe other, the Ricci tensor or Weil tensor, which can somehow be written in somehow through some field redefinitions in terms of standard. In terms of, say, like Einstein gravity plus some other fields.
Yes, there might be. So what if you, of course this particular derivation really depends heavily on the fact that this is the Ricci scalar.
No,
Okay?
right, yeah, sure.
So if you would add Weil tensors or Riemann squared or whatever,
Yeah.
there are of course always field redefinitions that you can do and try to get rid of them, but and I think there are some, if I remember correctly, there are some papers in that have written about what you can do maximally, about getting rid of all these things, and I think there are some results that claim that you can always. You can do a lot. I don't know. I shouldn't say things that I'm not certain about. So, but I think there have been papers written about this. So you should check.
You consider that.
Yeah.
If you want, I can make a comment on this point. So you can make this chain because when you have Ricci scalars, you have only the conformal factor of the metric.
Right.
So when you quantize something with spin 2, like with invariance under diffeomorphism, you have the graviton, and if you want, the graviton is described by the Weil tensor square. So the Hessian of the Weil tensor square is the propagator of the graviton,
Right.
while everything which has only Ricci scalar is the propagator of the conformal mode. For example, in 2D there is no graviton but only the conformal mode. So this chain obviously it's valid because if you're just rewriting something which has only a scalar degrees of freedom. But if you do real gravity, then you have the graviton. This is like gravity without the graviton. If you put inside the graviton, this chain doesn't work anymore. And
No, you have to do something else, clearly.
yeah, you cannot do it because you cannot take away the
No.
gravitational wave. So you will
No.
always have two indices. So
No, that's
you
true.
will always reconstruct the Weil tensor. So, and this also links to the fact that now we said that alpha has to be, if alpha is big, then I have also the other curvatures.
You would expect the
But
other.
then I immediately expect also the Weil tensor.
Yeah, in principle,
Oh, yeah,
yes.
and this-
No, in fact,
I will say that
I
this
agree.
is already like, it's back the tail of the reasoning. And then there is another point I think we should consider that we want to do inflation, so we want to do the spectrum, so we want to do the linearized equations to see, because we want to have fluctuation induced by quantum fluctuations. So it means that in the UV we want to quantize something. If we quantize something, then this kind of reasoning also has to be questioned if, because this is true at the classical level.
this is all through the
But if I
classical
do a
level.
path integral or something, I may have, for example, a Jacobian
Sure.
or something. So these f of r kind of chains are usually good at the classical level, but now when we want to do inflation, for example, and compute, we need to quantize.
Right.
So it's another point where I will say it's a little bit slippery to do just blindly
Sure.
this kind of reasoning.
So the whole point of this discussion is purely classical, okay? So this relation is purely classical. What happens if you turn on, if you think about quantum effects, that's a completely different story.
Yeah, but
And
then
you would expect all hell to break loose if this is order one.
yes, for sure, but
Yeah.
we are also writing down the R, which is a ratio between quantum amplitudes. So we can,
Oh, no, so
So-
I haven't, yeah, sure, but, okay, so.
so how is this consistent in any way?
No, okay, good. So, okay, think about it in the following way. So I know that this, okay, so strictly speaking, what happened here is the following, okay? I know that this is equivalent to this scalar field action and this potential, okay?
Yes.
Now, if I have a scalar field action, I can look at this and then quantize it, okay? And then I get these expressions.
No, I mean, I
Okay,
know.
and then of course I completely agree with you that if you would do it on this level,
Yes.
it's a bit, that's tricky. Yes. Okay. So these expressions, yeah, they are, strictly speaking, they have been derived from this action, you could say.
Yeah,
I know that I think, well, in the past people have done it, I think, for just starting here, but that's I agree with you that it's a bit.
But you are saying that if I do the perturbation of R, I get something different for R.
I mean, the perturbation is quantization procedure, so you cannot,
Sure.
this chain is not anymore valid at the quantum.
Well, you know, you can try to. In principle, you're right, but you can still, even if you. I mean, we can still. We already know that there's a quantization issue in just a linear. If you just have the Ricci scaling, okay. But we can deal with that by just assuming that these fluctuations are small and expanding around a classical background. So you could play that game. In principle, you could play that game here as well with r plus r squared. The only difference is that for this to work, you need this alpha to be big. Okay, so that's the only thing that's a bit tricky in that case, I would say. But formally, you can still technically proceed and get these results. Okay. Now, there's one more thing I should say about these results, and that is that you see n appear in here. Okay, and n is the number of e-folds. Okay, so these results for the departure from scale invariance and the tensor to scalar ratio depend on how many e-folds you need. And well, typically for the results that I will quote later on, you need about 55, 60 e-folds. That's the number we will use. Okay? So we'll always put n equals 60 or 55. It is, however, interesting because this is not always true that the departure from scale invariance is parameterized as 1 over n, or for the tensor scalar ratio as 1 over n squared. The fact that it goes as 1 over n for the spectral index is interesting because 1 over n is naturally a small number. So people have actually thought about this seriously to try to look at inflation try to study inflationary models from the point of view of this 1 over the number of e-faults, because that's a small number. Okay? So I will probably briefly come back to that also later. Good. So if you haven't seen this, you know, this is the story about f of r, gravity, and how it is connected to non-minimal models, non-minimally coupled scalar field models. Now, so why did these non-minimal couplings suddenly get some renewed interest? I think indeed, as Martin already mentioned, Higgs inflation is one reason. So if you want to make Higgs inflation work, so take the Higgs potential and then extend it to large fields, then you better introduce a non-minimal coupling to get inflation. I think the Planck sweet spot has something to do with it, the fact that, you know, over here seems to be a good region to sit with your models. The 1 over n expansion, the expansion in this small number, 1 over the number of e-faults, that's true for not just the Starobinsky model, but for all these non-minimal models in a particular limit, as we will see. And in fact, that's connected to this statement that these non-minimal models, if you add a non-minimal coupling, then there is some interesting behavior for any scalar potential or conformal factor that you add. If it satisfies some particular properties that I'll point out, then there is a universal strong coupling attractor. So all these models in a particular limit give rise to the same predictions, which is a nice organizing principle. And I'll briefly show that to you later on. And then finally, people have also been interested in particular this group, Kellos, Linde, and Roest. Roest, it's always the same people that you see here, but they have been very active in the last 2 years in trying to, you know, revive this program, and they've also been looking at the embedding of these kinds of non-minimal models in superconformal gravity. This is something that I will not discuss today. It will take us too far. So this is the kind of plot that has been produced by these people, Kellos, Linde, and Roest. And what is interesting about this is that actually if you add this non-minimal coupling, and if you take this non-minimal coupling and go to large values of it, all these models go to the same point. They all end up on this, what is known as the Starobinsky point. Okay? So it's a nice organizing principle. For large values of this non-minimal coupling, all these models end up in this point, which is also in the sweet spot of the Planck data. Okay, good. So how does that work? How do we end up with a strong coupling attractor in the plot that I just showed? So just to explain to you a little bit more about what happens in the strong coupling limit. So here you see this action that I already showed to you before, and there's a couple of things that you should keep in mind, or a couple of boundary conditions of these actions, and that is that actually what you'd like is that in the vacuum, phi vacuum, the low energy vacuum, this thing should be 1. This thing should be 1 because we want to get back the Planck scale, okay? And which we picked to be 1. So we're going to make sure that this happens, and then we're also going to make sure that the potential at phi vacuum is 0. Keep that in mind. Now, what you can do if you see an action like this, you can just transform, doing a field redefinition, redefining your metric, to go to the Einstein frame. So this is the Jordan frame, this is the Einstein frame. And what happens in that case is that the potential changes by u over omega squared, but your kinetic term also changes. You get 2 contributions from the determinant, essentially, of the metric, and also from R itself. Okay? You expand and rewrite what happens if you redefine your metric. You get 2 terms, and these are the 2 terms. Okay, good. Now, what you can see and how we analyze, and I'll describe this for you in the way we analyzed it. This is not what you'll find in Carlos, Linde and Roest, for instance, so I'll just repeat their story because they were the first one to figure this out. Well, I'll use my method, my approach, because it will come back later when I talk about the weak coupling limit. So there are basically two regimes if you look at this action. There's one in which this term is dominant, and there's one in which this term is dominant. And we'll later see that they can be connected to large coupling or weak coupling. Okay? So we call this the steep limit, so we'll analyze this very generally. The steep limit of this omega, this conformal factor. So that means that omega prime squared over omega is much smaller than 1, much bigger than 1. Okay? That's a steep limit in the sense that this omega function, omega phi, has a large derivative. Okay? So if this is true, then this term dominates in this kinetic, this new kinetic term. And you can also show that the slow roll parameter in the Einstein frame looks like this. So in this limit, the slow roll parameter epsilon looks like this. If you want to get inflation, you better make sure that the slow roll parameter is small. Okay, very small. And that means that this U, this potential U, has to look like this. If it looks like this is going to be small. There is a region in the potential for which the epsilon is very small. Okay? So now what we've seen is that actually this U has to be of this type, so it's now connected to the conformal factor. U is lambda times omega minus 1 squared. It's connected to the conformal factor, and in that case you can always find a regime where you can get inflation. Okay? Good. But I noticed that I haven't, this is the only relation that I've now given. Okay? So omega is completely free. I haven't said anything else about omega. It can be an arbitrary function. In fact, if that's the case, so if this kinetic term is dominant, you can show that the canonically normalized scalar field, because what you can do is transform to a canonically normalized scalar field, but this is a half, is exactly of this type. Okay? So the canonically normalized scalar field psi is related to the log of omega. Okay? So it doesn't carry any information. I mean, in some sense what this means is that any information on omega is more or less lost if you do the transformation to the canonically normalized scalar. And for all models, independent of omega, so independent of what kind of omega you have, you get this potential. Okay? So that's the funny thing that goes on in this particular case. No matter what omega you have, you'll always end up with this potential if this is dominant, if this holds. Okay? And this holds. Okay? So all information on omega is lost, and this is in fact exactly what I showed you before. It's the Starobinsky potential. Okay? So what I think I've shown here, is that actually if this is true, then you always get Starobinsky. You always get Starobinsky independent of omega. You can pick any function you like. Okay? So, to give you a bit more, so this was very general, to give you a bit more information or to give you an example, so you can take omega to be 1 plus psi times f, where psi is now the non-minimal coupling. Notice that phi vacuum in this case equals, so if you want this to be reproducing the ordinary Planck mass, then what you would like to do is f of phi should hit 0 at phi vacuum. Okay? This is called universal attractor and a universal attractor model. So this f is completely arbitrary, this function f. And the other example is what is known as induced inflation, where you lose the 1. These are very different because the vacua are different. Okay? If you want this to be 1, then you better make sure that at weak coupling, when psi goes to 0, then this better be 1 over psi, this f of phi. So these things are very different, and that's important because they also will show very different behavior at weak coupling. Now to be even more explicit, you can take this f of I to be a power law. Take this to be a power law. Well, then for n equals 2, this is Higgs, the Higgs universal attractor. For n bigger than 1, for all big n bigger than 1, the universal attractor models violate perturbative unitarity before hitting the Planck scale, as opposed to induced models. So what do I mean with this? Okay, there's a couple of things. So basically, what I've just shown on the previous slide is that for psi, if you take this psi to be very big, take this psi to be very big, the coupling to be very large, you will always satisfy this condition. This condition is satisfied for psi very big, both for this model and for that model. Okay? So that means for psi very big, these things all end up at this point. Okay? So here you see an example again in this plot. You start with some, this is for this case, the universal attractor. Here you start with some, this is 5 to the 4th, and you increase the coupling chi, and you will end up at this universal attractor. This will happen for all powers of n. Now, one thing that you should be worried about, in particular also, this is something that people were worried about for Higgs, is can you really trust all the way from the vacuum, the honest to God vacuum, all the way up to very high field values, can you trust the physics? And one way to test that is to see whether perturbative unitarity is violated before you hit the inflationary scale. Okay? Before you hit the Planck scale. Now, how do you do that? You just look at the Einstein frame potential that you get, and you're going to look for positive powers of this psi, and those will influence, basically, this will tell you the scale at which perturbative unitarity breaks down. And what you see is actually for these models, universal attractor models, you'll find that actually it breaks down before you hit the Planck scale. Okay? So this is bad news, because in some sense what you would really like to do also for Higgs is really trust the potential all the way up until the Planck scale or the inflationary scale to be able to say something about the inflation going on at these very high field values. But this doesn't work apparently. It does work for these induced models. So if you take these models, then you'll find that actually there are no positive powers of psi if you do this properly. And perturbative unitarity is, is fine all the way up to the Planck scale. So for these models, where you lose the 1, you actually find that there's no problem with perturbative unitarity being violated at the scale below the Planck scale. So you could get away with trusting this potential all the way up till the Planck scale. No matter what you do in both of these cases, you find that there is this universal strong coupling attractor for chi going to, chi much bigger than 1, will end up here. Okay? Now, one way to think about this is that you get universal inflationary behavior due to large stretching. Basically what happens is that if you take this limit where chi goes to infinity, where chi is much bigger than 1, you're going to zoom in on a very short region of your potential. Okay? Because this is a conformal factor, more or less. So if you could make this conformal factor very big, then basically what you're doing is you're going to zoom in on a very short region of your potential. So that means that even, and if you then transform to the Einstein frame, what you see is actually that even very steep potentials, because you zoom in on a very small region, can give rise to inflation. Okay? So this is one way to think about it. Okay, so we've shown, this is just something that was known before we started to do our work. How much time have I got left? Okay, good. And then I picked up, I had a conversation with Diederik Roest at some point. And it's clear, but if you look at this picture, that for these models, because this is what is plotted, these models are plotted here for different powers of n. You see that actually if you go to weak coupling, basically that makes perfect sense. For weak coupling, if you take away this coupling, This is just reproducing the minimal results. Okay? This is what the well-known results by taking away this coupling. So there is no attractor behavior at weak coupling. It's just they all are different. Okay? They're all different. However, speaking to Diederik, he suggested that actually, perhaps in this case, there might also be a weak coupling attractor. And that might be interesting. So I was a bit triggered by this remark, because if that were the case, then maybe you go from this strong coupling fixed point to a weak coupling fixed point, and you could stay within this kind of nice region of Planck. Nevertheless, I mean, even beyond that, it might be interesting to find models or subsets of models that have both an attractor at weak coupling and at strong coupling. In fact, I remember saying to Diederik, well, that cannot be right. I mean, that would be too good to be true if there were two attractor points. I mean, it would be too nice. But then I didn't see him for a while, and I mentioned this to my PhD student, and he started to go to work. And at some point he stormed into my office, and he said, I think Diederik might be right. So we thought about it a bit, and then we came up with a similar kind of argument that I already presented for the strong coupling case. So we can start out really very general, and what you can do is you can say, okay, let's look at the other extreme. So instead of this thing being dominant in this kinetic term, you can look at this part being dominant. So what happens in that case? So we call this the flat limit. It's flat because now the derivatives of this conformal factor are small relative to omega itself. It's kind of a slow roll limit for conformal factors. So again, if you do that, you get a nice expression. You get a nice expression for the slow roll parameter in the Einstein frame. In fact, it can again be satisfied by picking a U which is of the same type, which is nice because it's the same type means that this is the same type that will also give you the strong coupling, Starobinsky attractor. Okay? Good. So that's the first good news. You can get inflation to work at small coupling, at small nominal coupling. So now let's see what happens. Do all these inflationary points end up being an attractor? In other words, we end up at the same point. Now what you can do is you can actually say, okay, let's expand this omega around this small value. Basically these omega primes have to be very small, so we can do a Taylor expansion. And we can assume that actually all derivatives, actually the assumption that goes into this is that the derivatives of this omega actually become smaller if you go to higher derivatives with a small parameter alpha. So if you do this, if you expand u over omega squared, assuming this is true, and doing this expansion, in the Einstein frame you get the following expression. So if the first derivative of this expansion around the vacuum value, so omega vacuum is what I have expanded around, so this is the first Taylor expansion around the point omega prime, times chi squared. So if this omega prime is non-zero, this is just quadratic chaotic inflation. Okay? This is just chaotic quadratic inflation. And these higher order terms, they're all smaller because they depend on higher derivatives or more powers of the same derivative. Okay? And I've assumed that these are all smaller. So these are suppressed and these are even more suppressed. So we see that actually we can show that in this limit you end up with just chaotic quadratic inflation. Okay? You also note that in fact it does depend on the details of omega prime, because omega prime is still written here. Okay? So if you take different omegas, you also get different derivatives, and you get a different effective potential. Okay? So it's not immediately clear that you will get the same predictions for NS and the tensor to scalar ratio, but however, it turns out that for chaotic inflation, this just sets the scale of inflation, but it doesn't but it doesn't, I mean the slow roll parameters will not depend on it, actually, turns out. I'll show you this soon. So, as soon as you have a non-vanishing first derivative, you get quadratic chaotic inflation. Higher order powers are small due to the flat conformal factor, so these are all suppressed because this condition holds. Chaotic predictions for NS are universal. In other words, even though this depends on omega prime, the slow roll parameters don't depend on this. That's just a property of chaotic inflation. But the scale is dependent on the derivative as compared to steep limit. Okay, this is an important point. So if you take the previous limit, in a strong coupling limit, this would be the potential. And the potential only depends on lambda. It has no information anymore about omega. It only depends on lambda, which is basically the overall scale set by this potential u. Okay? Here, there is information in this effective potential which depends on omega. It doesn't affect the slow roll parameters, but it does affect the mass of the inflaton, the effective mass, which is important because it sets the scale of inflation. Okay? So the slow roll parameters NS and T, they are universal, but there will be a distinction in if you add another parameter, namely the scale of inflation. So in that sense, this universal behavior is a bit less universal. Okay? Is that clear? So, here are some examples. This is basically the upshot of the story. If you would take, let's see, so if you would take an omega conformal factor that looks like this, where basically what I've done, I've expanded around a new field phi tilde, and these alphas are the small parameters, and these omega m's are basically the Taylor coefficients. Then you can show that indeed epsilon and eta only depend on, they don't depend on the details of this omega, they just depend on omega tilde squared, and eta is just 2 over omega tilde squared as well, if the first derivative is non-zero. If the first derivative is 0, then you go to higher order chaotic models. So in fact, for instance, if this would be 0, then you move on to psi to the third. Okay? So you can get higher order chaotic models as well. So how can you understand this in a small coupling limit? Well, again, take these, so we can now take a very specific example. This is again induced inflation with this non-minimal coupling psi. And now take for this f of phi, take phi to the power n. It's the simplest situation. Then you get this effective potential. Okay? And you see that there's dependence on m. Okay? This potential depends on m. However, the slow roll parameters do not depend on this. That's just a feature of chaotic inflation. So you can actually make this interesting plot. So you know that for these models, you also get the strong coupling attractor. So you go from a weak coupling attractor, which is just chaotic inflation, to a strong coupling attractor for different values of m. Okay? So there's an attractor at weak coupling and there's the attractor at strong coupling. This is in real space, this is in logarithmic space. Now, in fact, I came back to Diederik with this result, and I said, listen, I think we nailed it, there is indeed this weak coupling attractor, and then Diederik said, yes, I know, because we also worked on it. So, similar results were actually achieved also by Carlos, Lin, and Roest, so you can find those in their paper. We published on the same day. We agreed that we would publish on the same day. So, I think the analysis that we did is a bit more general, but you know, I say this on camera actually. But nevertheless, the results are the same in practice. Okay. So,
So in the intermediate regimes, this omega prime will not be very small. It will be like.
No. So if you look at this, so this is the parameter that's running in this case, psi.
Yeah.
So it starts at 0 and then it will.
So does that mean that you will have some stronger, let's say, how do I say, scale dependence, or in your parameters of in your model, basically? I mean, now you have only shown us the extremes, right?
No. This is this is numerical work.
Right.
This is This is not the...
Yeah,
so-
sure, I know,
okay,
but
good.
I mean, at some scale, right?
Right. At what scale? No, this is not at some scale. Psi is running here in these plots. What do you mean?
Yeah, I understand, but when you show us the effective potential,
Yes, that's at
You're
a
showing
particular
us-
scale.
you're showing it as in some specific limits, right?
Right, this is at a particular limit, yes.
In the intermediate regimes, I cannot write it like that.
No, definitely not.
And then the omega prime will not just will not be very small, right?
No, this will not be true.
Yeah. So then I imagine that all of the parameters in my theory will be strongly field dependent. Oh no, maybe not. I don't know.
No,
I'm
no.
asking.
I mean, okay, so I think you should realize that all I've been doing here, I've not been considering fine-tuning issues.
No,
This is
no,
just our class.
I understand.
So the only thing I cannot say for the intermediate region
Mhm.
is what this potential looks like. I mean, all others will become significant.
Yeah, and the field dependence on, you don't even know how the potential looks, but say you wrote down a potential at some, at some scale,
Yes.
then the parameters in that potential would be field dependent, right?
Yes.
And that will not be like in the, and it would probably have a strong field dependence because it would not be in the omega prime being small limit, right?
Right. I
So
think
you would
so.
imagine that your theory changes a lot when you go from, say, 60 equals before the end of inflation to, say, 50 equals before the end of inflation.
This is okay. So also to point this out, this is at a fixed value of the total number of e-volts.
That's exactly what I mean. So
Yeah.
now you compare this to some data point and you will see something probably happens to the middle, right?
Oh, okay. So if you change, you get a band. Okay. So if you allow n to run from 50 to 60, let's say, if you
Right.
take this, then you get a bandwidth.
Right.
We haven't looked at what happens in the middle. That's a good question.
That's my point.
Yeah. Okay. Good. Now I understand your question. I haven't looked at that.
In the plot on the right, what is it?
Oh, that's just logarithmic. So the r is just logarithmic.
Okay.
Yeah, nothing. So I just copied it, but it's no meaning. So this is just the logarithmic plot, and this is just the real plot.
Okay.
So this runs. I can't even tell the numbers here, but I think it starts from 0.14 here. R equals 0.14, and this is.
You would get a very large running in your theory in the middle. You would get a large running in your theory in the middle. Because your
Right,
parameters are very
Yeah, I think so too. Yes.
That may not be bad.
No, I think that's probably correct. I haven't looked at that.
The value of
Or
R,
it could be in the middle of your onion.
Yes.
value of R, it's like 0.003 or something? What is
Yeah,
that?
yeah. The lowest one is 0.03.
Yeah.
That's Starobinsky. Yeah.
Okay.
Good. So these are some examples, some explicit examples that are nice to show. I think we generalized even more. You can do a little bit more and do the same analysis. One thing you can do, for instance, is in fact this also works. So just take lambda omega squared 1 minus. So for you, you don't have to take the value with n equals 1. You can actually take a free parameter n, where be equal to 2, 3, 4. It also works. And you get different models. In fact, for different values of n, you get different values of the chaotic attractor. Okay? So you don't get quadratic, but you get 3/2 chaotic inflation. So that's what you can show. In the steep limit, you basically get the same Starobinsky attractor. Even though there's this factor of n, it doesn't really make a difference for the attractor point. For the flat limit, so the weak coupling limit, you get the different chaotic attractors. So here, the green one is now with n equals 1, that we just showed. This is n equals 3/2, and this is n equals 2. So you can shift a bit. So now, they all have independently, for a fixed value of n, you have an attractor behavior, but it changes for different values of n. Just what might be fun to show, but that's...
Yeah, so then it looks like NS is growing with N, right?
right.
So what kind of running is that? If NS is growing, is that a positive?
You're saying as a function of...
Yeah, when I go from 60 equals before the end of inflation to say 50 equals before the end
Yes.
of inflation, then my...
But I haven't plotted it. This is not the number of e-volts.
Oh, what is that?
Sorry, this is at the new parameter small n.
Sorry. I
This is
didn't
the
follow
power of this, so this is different.
Right,
This
okay.
has nothing to do with the number of e-volts, okay? I haven't looked at what happens if you change the number of e-volts. Okay, good. So I think that's all I have to say. So just to summarize. Oh, this you can't really see it, but anyway. What we did was we derived general criteria for the existence of a chaotic attractor at weak coupling. We've shown that induced power law models, so basically where you lose the constant, so we have psi times some function f of phi, feature a chaotic attractor. And the scale of inflation distinguishes specifics of this conformal factor. So one more time, if you would actually add a third dimension in here, with the scale of inflation, then these points would actually be separated. Whereas the universal attractor would stick and remain at the same place. Anyway, that's I think important to point out. So I didn't discuss with you, but another thing that we noticed, of course, is that here, the approach to this fixed point is universal. It's always the same slope, which is not true for universal. And you might want to understand it a little better. Why is that? I don't know. We did not discuss superconformal gravity or string embedding. There's some interesting stuff going on in that direction. I didn't discuss with you fine-tuning, which is something that I'm worried about and I'm still talking about with my students to see if we can do something about this. That's all for the future. So, but for now, let me thank you for your attention and stop here.
So thanks very much. Other questions for you? No other questions? All right, well, let's thank Pieter again.